Hi students, let's look at this question which is on hypo testing. Let's see how we can do this proficiently. This question was taken from 2020 paper 2, question 10 of the H2 math paper. So carbon steel is made by adding carbon to iron. This makes the iron stronger, though less flexible. A steel manufacturing company makes carbon steel in the form of round bars. Okay? The process is designed to manufacture bars in which the amount of carbon in each bar by weight is 0.5%. Sorry, 1.5%. It is known that the percentage of carbon in the steel bar is distributed normally. Okay, if you see this word distributed normally, meaning you don't have to worry about using CLT. So you know the population is already distributed normally and the standard deviation is 0.09%. Okay, so after comments from customer, the production manager wishes to test at 5% level of significance if the percentage carbon in the steel bars is in fact 1.5%. So he examines a random sample of 15 bars. So this case here, 15 bars, and determine the percentage of carbon in each bar. Find the critical region of a test. Okay, great. So I'm going to name the distribution as usual, right? So it is known because H0 is where everyone agrees to be 1.5%, right? So you want to test it against whether it's actually 1.5%. That's the idea. So your alternative hypothesis is mu not equals to 1.5. All right, then I'm gonna list down everything down. We need alpha percentage, which is 5%. Then our n, we took how many bars? 15 bars. Okay, and after which we also have standard deviation, which is a population standard deviation of 0.09. Great. So there are two ways of doing this because you want to find the critical region. Now, understand that critical region is basically looking at the X bar. What is the tolerance level for the X bar, the critical region for the test of the X bar, right? So if you want to do it directly, you could do it like so. What it means is from this sample mean of 15, right? We know that always the assumption has always been that it will be 1.5% here. Okay, so this is normally distributed of 1.5. Then we know this will be sigma square because it's a sample of 15, so sigma square over n, right? Which is actually 0.09 square over 15. Okay, so this is the curve they're looking at. So what we need to do now is we understand that for the 5%, if we are looking at two-tail, okay, the closer you are to the mean, obviously the more true is H0, right? So 5%, meaning if you want to see whether it's accurate or not, you are splitting the 5% to two parts here. So this will be 2.5% and the other is 2.5% on the other end. Right. So your critical region would be this over here, these two parts here. So you can just inverse norm here and find out what is the critical region. So usually I will not encourage students to use inverse norm center because I find that inverse norm center, oftentimes students forget to take 1 minus of 5%. So if you want to use inverse norm center, you just take 1 minus 0.05, okay? But if you're careless, what I'll suggest is you just take 0.05 divided by 2. Then the center, we just put 1.5 over here. And after which this is a square root of 0.09. So this is square root of 0.09 square over 15. Okay, so that's the distribution you're looking at. So you put left tail, so you get that this is 1.45445 over here 1.45445. All right, then you could obviously use symmetrical values to find this, or you could just inverse norm on the right. You get this value here, 1.54554. So critical region will just mean that you are rejecting H0. So there you go. Hence, you can just write the critical region. Critical region will be the sample mean has to be less than or equals to 1.45, or bar x is at least 1.55. Okay. So you know sample mean is actually, this is in percentage, so we could just add the percentage. So you just add a percentage there, it will be 0, because percentage cannot be less than 0. Okay, or it could be more than 100%. So that's how you find the critical value using method. Of course, you can use basically the z-test, which is to use the standardized curve to actually find the critical value. But just remember to basically find the range of bar x. Basically, what it means is if you want to find the critical region, you're finding the range of value of bar x when h0 is rejected. So I'm gonna just do that. So if you're going to use z-test, z-statistic, the test statistic, so this will be just be using z normally distributed 0 and 1. So you just find the z critical values. That will be inverse norm. You put this will be 0.025. And then you put like 0 and 1. I'm gonna just use okay, right tail is fine. This will be 1.9599. So this is 1.95996. So then this will be the negative of it. It will be negative 1.95996. Okay. 95. So to reject h0, we know that essentially z statistic has to be at most negative 1.95996. Okay. Or basically z statistics will be more that the z stat have to fall within the critical region, right? So that will be 1.95996. Okay, then just carry out the test here. So we just standardize the z statistic here. So the what do you call it? The x bar minus 1.5, which is the mu, then divided by sigma square over n. Then we're just gonna find the range of bar x. Just multiply this positive value over with negative 1.95996. Okay, so you just solve this linear inequality. So the critical region, similarly, your x bar cannot be less than 0, or it has to be, it's a percentage, so it's between 0 and 100. So you just add the lower bound and upper bound. Okay, so that's how you do the first part here. So let's look at the second part. After comments from the customer suggest that these bars are not sufficiently flexible, so which makes the production manager suspect that too much carbon has been added. Oh, sorry. The company recently launched a new line of flat bars made from mild steel. In the mild steel, amount of carbon in each bar is weighed by 0.25%. So as what do you call it, as compared to 1.5% of carbon steel, right? So the comments here, he decides to perform a hypothesis test on a random sample 40, right? Because the customer suggests that these are not sufficiently flexible, which makes the production manager say that too much carbon has been added, too much. So supposedly the new the new amount should be 0.25%. So he decided to perform a hypothesis test on a random sample 40 of a new flat bars to find out if this is the case. So explain why the production manager takes 40 flat bars for this test. And he only took like 15 bars earlier. Okay, the reason is because the main thing is because the carbon steel, the percentage, right? The population distribution is known to be normally distributed. Okay, this is a new product. You don't know whether the population is like the what do you call it, the mass of the percentage amount of carbon for this mild steel, is it like normally distributed. So that's why you need to take 40 so that you can invoke central limit theorem. Okay, so that's the idea there. So just write it down. So this is how I write it. Okay, so in the earlier test, the percentage of carbon in the carbon steel is known to be normally distributed, whereas the percentage carbon in the mild steel is not known to be normally distributed. So you need a large sample. In this case, for the bus, a large sample is required so that the sample mean will be approximately normal by central limit theorem. So that's how we do part 2. Let's look at part 3. Part 3 said the amount of carbon X% in a random 40 flat bars is assumed to be below. So this is N40, then summation, and so on. Calculate the unbiased estimate of population variance and mean. I think this is pretty okay. Just use formula. So the formula is found in the MF 26 or 27 for this. So what you're gonna do is just plug in the value and just plug and play. So this is the answer. Let's look at the next part. Test at 2.5% level of significance whether the mean amount of carbon in the flat bars is more than 0.25. You should state your hypothesis and define any symbol that you use. Okay, great. So we're gonna just write everything down. So you want to test whether the flat bar is more than 0.25%. So you H0, initially you know that this is 0.2 mu should be 0.25%. This is what is believed to be true, right? Everyone assume that it's 0.25%. H1, your mu, you want to see that whether the alternative hypothesis should be more than 0.25. You just look at the X bar. Yeah, this X bar is more than, because it's one tail, it only makes sense if it's on the right tail. Okay, if you're not sure, you can just look at that. So that's that. So I'm gonna write down all the things we need. So these are all the things we need. Then under H0, I'm gonna use a test statistic Z test. Actually, this could use p-value, but we need to invoke CLT for sure. Okay, there's that. So approximately by what do you call it, central limit theorem. Then we're just gonna find the p-value. P-value, what we need is actually go to statistic, then calculate test Z test. I'm gonna put in mu is 0.25. Then sigma is actually the root of this value here, so it's 1.46205 times 10 to the power negative 4. Okay, then oh, shouldn't use list, I should use statistic, sorry. Then our X bar will be 0.25, 0.254, right? Yep. Then N is 40. And we're looking at the right tail, so calculate the p-value. So this is the p-value. So this p-value, we just need to see whether this is more or less than alpha percentage. So this is actually lesser than 2.5%. Right. So you reject H0 here. Then we conclude based on the in context of the question. So since p-value is less than 2.5%, hence we reject H0 at 2.5% level of significance, we have sufficient evidence to conclude that the mean amount of the carbon in each flat bar is more than 0.25. Okay, so in favor of the alternate hypothesis. So that's how we do this question proficiently. If you have any questions at all, please do let us know, and I'll see you in the next question.